Hello, everyone. Welcome back. Today, we want to talk about, as it says, introduction to probability. Give you an idea what probability is, what we mean, and understand some of the basic rules and concepts, and do some of the basic ideas. So as it says, our goal is to understand the basic concepts and rules of probability, be able to calculate some basic probabilities, and then also understand one of our first important idea is something called a complement, how it's used in probability. So let's talk about kind of what probability is. This isn't really so much a definition as just saying the reason. So the goal of studying probability is to quantify the likelihood of something happening with the ultimate goal of predicting outcomes. So it says we'd like to say, try to come up with some kind of way of expressing in a number how likely something is to happen. And that's called, one way of doing that's called the probability. So you have to have some understanding of what's happening, kind of the process, what's going on to be able to do that. And our goal then is to be able to use that information to predict something in the future, predict what will happen when we do this process over and over again. The probability is used in lots of ways in real life. One way can be, if you imagine if you go to Las Vegas and gamble, then probability is used in determining the outcome of those games. And you've heard the expression, the house always wins. Well, that's not true that always wins, but winning is based on probability. The idea that in the long run, even though some people will occasionally win every now and then, in the long run, more people will lose money than gain money. That's why casinos make money. Also, this thing is true of the lottery. Some people get big payouts, but you have to have more money coming in the system than you have going out in order for it to work. And also, another way probability is used in our lives more commonly is in things like insurance, life insurance, health insurance, car insurance. Basically, companies, which are businesses, and their goal is they have to make a profit to be a business. Then they have to make sure that they have more money coming in that's going out in settlements. So they use probability to help them make those decisions on how much to charge. So that's one way, it's common ways it's used. Let's talk about some basic ideas of probability, some basic definitions. The first is an event is any collection of results or outcomes of a procedure. Okay, so let's go over here to the right. As we introduce these things, we'll talk about them. Sorry, accidentally kicked out of the sharing screen. Well, let's look at some examples. Okay, so think about events. So one event could be the outcome of flipping a coin. Okay, or rolling a die. Okay, so singular of dice is die. So if you think about a six-sided die, so the events here would be the outcomes of those. The outcomes of flipping a coin, okay, heads or tails. The outcomes of rolling a six-sided die would be the numbers 1 through 6. Okay. Now, a simple event is an outcome that cannot be further broken down into simpler components. Okay, so simple event for these examples would be like getting heads or tails. That's a simple event in the sense that that's the only, we can't break any one of those down either further, or getting, for rolling a die, getting the number 1 through 6. Okay, those are the simple events. Now, the more important idea, which is based off those, is something called the sample space. Let's talk about that next. Okay, so the sample space, as it says, for some procedure, consists of all possible simple events, basically all possible outcomes. That is, the sample space consists of all outcomes that cannot be broken down any further. So most of the time, we'll think of your sample space is all the possible outcomes. Of any event. Okay, so for flipping a coin, and a lot of times we're at the sample space, these kind of squiggly brackets. So you can either get a head or a tail. That's your sample space. That's what could possibly happen. Okay, and those are also the simple events. And then for rolling a die, then obviously then your numbers, you get the numbers 1 through 6. Your sample space consists of the numbers 1, 2, 3, 4, 5, and 6. Okay, and you think of other types of probabilities. Anytime your list of possible outcomes, that's your sample space, and that's very important to understand. You understand what can possibly happen. Then, based on then what can happen, then our next goal will be determine then the probability of each one of those outcomes happening for the sample space. Now, a few ideas of notation. It says below. So we're going to call probability, this is just common notation, not the only way it can be done, it's the way it's commonly done. P denotes probability. So I say the probability of something, then we use the letter P here in this class and for other, often in other classes. And then A, B, and C denote specific events, okay? So for example, I could say the probability P of H would be the probability of, in flipping a coin, getting a head. Okay, so I'd read it that way. All right, so the probability of getting a head is, that's the way it's read in basic words, and that would be 1 out of 2. We'll explain what this means later, why we get that. Basically, it's 1/2 or 1 out of 2. Okay, or if I think the probability, let's say the probability of P of 5 or a dice, that's probably of the probability of rolling a 5. Okay, and as we'll see in a moment, that's going to be 1 out of 6. 1/6. Okay, that's what the notation means. So the part of the sample space, the outcome we're looking for is within the parentheses. We said the probability of that then is then whatever, as we'll see, the probability turns out to be. That's the notation we'll use. Now let's talk about the next, about kind of the common ways to determine probabilities. There are kind of 3 main ways. Number 1, we call the relative frequency. Okay, and this is essentially kind of the experimental way. All right, what we mean by that, let's read this. So the relative frequency approximation of probability, it says conducted or observed procedure is basically, so the probabilities we'll see as a fraction. So the number of times occurred over the number of times the procedure was repeated. Now, the number of times the procedure was repeated, we think of that being kind of like our sample space. So basically, it's the number of times, whatever outcome we're looking for, over the number of times we did it. Okay. So let's give an example of that. So let's say we have this example, and I'll make up one. Let's say we have, let's say that Apple tests 1,000 iPhones and 3 are defective in some way. Okay, they have some kind of problem, so they can't be sold, they have to be fixed. Now, I'm sure their standards are better than, they're probably, defect rates probably smaller than that. Let's just use that for example. Okay, so then the probability of being defective, okay, is going to be, so the number of times something occurred, a defect occurred, which is 3, then divided by the number of times the procedure is repeated. So let's say you're testing these things as they come off the assembly line. You test 1,000 of them, and 3 are found to be effective. Then your probability then is 3 out of 1,000. Okay. And so if you calculate that, that's just, I'll put that as a decimal. That's going to be 0.003. Then that's a probability of being effective. Now, as we'll talk about here a bit later, then the probability of not being defective, then you think about that. Well, that's actually what's, so the other 997 are not defective. So the probability of not being defective would be 997 over 1,000. We'll talk about that idea here in a moment. Okay. So that's one example. Another example we think about is flipping coins. So let's say, I should make this, actually, this is example number 1 up here. So number 2, let's say we flip, we expect, as you probably expect, flipping a coin, you expect if it's a fair coin, you expect to get approximately, no, not necessarily exactly, 50 heads and 50 tails. Okay. Let's say we flip a coin 100 times. Okay. Then we get 47 tails. Okay. So we do that then. So the probability then of getting a tail based on this is, so the number of times something occurred, so 47 tails out of the 100 flips. And so that then is 0.47, about 47% of the time. So that's based on an experiment or it was observational, or a lot of times these are based on just observations, not just experiments. And once again, this is, as I mentioned before, how insurance companies use probability. This is often what they use. Well, they'll look at, based on historical data, what they have in the records, of probability of accidents, maybe like a car company or a car insurance company. Then they'll look at the probability of certain accidents. Also will determine then, based on the probability of those accidents, also how much on average each accident costs in terms of damage to the vehicle. And then that's how they use that information then to determine car insurance rates. But that's more of, that's not an experiment, that's an observation by observing the data that's available. Okay. So this is, once again, relative frequency probability. We're kind of a observational or experimental probability. So we're looking at data, okay, and information, or doing an experiment to find out. Now, the second one we'll mention is called the classical approach. So the classical probability, I'll just call it that. And what classical probability is it says this requires equally likely outcomes. Okay, this requires equally likely outcomes. So an example of this would be, as you just mentioned, flipping a coin. So as far as our examples, number 1, so you flip a coin. Okay, say it's a fair coin, so each face, each side, is equally likely. Okay, so then based on that, then we can say then probably here is the same format. So it's essentially all these probabilities essentially boil down to these types the same way, or basically the basically the numerator is what kind of event, what it is you're looking for, and then basically the denominator is your all possible outcomes. So basically it's the division of the outcomes you're looking for divided by all the possible number of outcomes. Okay, so how many outcomes you want divided by how many outcomes there are. So here, then the probability of getting ahead, okay, is, so if each flipping a coin, each face is equally likely, there are 2 possible outcomes. So there's one outcome we want, ahead, out of 2 possible outcomes. So our probability is 1/2 or 0.5. And the same for a tail in this case. The probability of getting a tail, there are 2 possible outcomes, a head or a tail. There's only one of those we want, a tail. And so it turns out that's exactly the same probability, 1/2 or 0.5, or about 50%. Okay. And we think about as well, I was going to turn that idea rolling a die. And I said these are all equally likely. Okay. And so if we said each side is equally likely, so each side is equally likely. Write that better. Okay, and then there are 6 sides. So let's say the probability of getting a 5, rolling a 5, was, and this, so there's 6 possible outcomes, numbers 1 through 6. If we assume they're all equally likely, probably getting any one particular one is just 1 out of 6. That's also the same for the rest of them. Okay, so probably getting a 1 or 2, any individual one, assume they're all equally likely, is the same. Now, once again, you can see why this requires equally likely outcomes. If this was a loaded die, you've heard of loaded die before, or one side is more likely to come from the others, then this no longer works because it's not going to be 1 out of 6. Okay, it's not all equally likely. It's still possible to determine the probability in those ways. In fact, that's where you might be able to do an experiment to roll the die many times and see if there's one side comes out more likely than the others. But this kind of probably here doesn't work with that. Okay, and also 1/6 is approximately, not equally, but divide 1 divided by 6, that's about 0.17 or about 17% for each side of an equal, of a fair die. Okay. Now, the third one, I'm not going to write anything down. That's the one we're probably going to talk about, probably no more than here. It's called subjective probabilities. It's estimated by using knowledge of relevant circumstances. So this might be someone just kind of using their knowledge, based on the experiences they've had to say the probability of something. Okay. So maybe in sports, you might say that, well, probably winning this game is probably 10% or less. Okay. That might be based on what you've seen this particular team do or the teams have to play or some other things. A lot of times this is why we're not going to spend much time on it because it's subjective. This isn't really based necessarily on data or an understanding, a theoretical understanding of the problem, just more based on knowledge. And then sometimes that subjective, it may not be that reliable of a probability. It may not be that reliable or useful in predicting outcomes. Now, another important concept in probability. In fact, actually, I'm going to skip ahead right here and actually go back to this law of large numbers. Let's go into this part next. In fact, range of probabilities. Okay, so understanding the range of a probability. And you say probability, make it singular. So once again, for probability being P of A, so let's call this P of A, once again, which is the probability of event A, whatever event A is, then the probability is going to be between 0 and 1. And this will also think of this as being 0%. We're thinking in terms of percent and 100%. Okay. Now, 0 is impossible. Okay. So 0 is impossible and 100% is certain. All right. So if something's impossible, like saying a 6-sided die, what's it possibly rolling a 7? Well, there's no 7, so that's impossible, right? Now, certain, if I say flipping a coin, if I say, well, I don't care if I get a head or a tail, then I'm certain to get something I want, right? There's a 100% chance of getting a head or a tail, one or the other, because you're going to get one, either head or a tail. So that's certain. Or also up here with rain, a completely sunny day with no clouds, there's 0% chance of rain. As long as you'll see forecasted 100% chance of rain, that means it's definitely going to rain. So basically, then probability is always between these two numbers, either between 0 and 1, including possibly both 0 and 1, but usually between. So sometimes you'll see people being a little careless. You'll say there's a 200% chance of something happening. Well, that doesn't make any sense. Probability is always between 0 and 1, or between 0% and 100%. Now, let's come back to this topic. We skipped over something called the law of large numbers. Let me just read this. So the relative frequency approach, like the first way to calculate it, like the example of the iPhones, is an approximation. As number of observations increase, the approximation tends to get closer to the actual probability. This is known as the law of large numbers, which says this: as a procedure is repeated again and again, the relative frequency probability of an event tends toward the actual probability. So what does that mean? Well, what it means is that For example, we said the idea of think about a coin. We assume most coins are fair, right? You have an equal chance of landing heads or tails. What if you didn't know? What if you expected that a coin wasn't fair? One way to test that would be to flip it over and over again. You might need to flip it many times. Now, the more times you flip it, you say flip it 10 times, you're getting some idea. If you flip it 100 times or 500 times or 1,000 times, the more often you flip it, the more times you flip it, then the ratio of heads to tails should actually get closer to the actual probability. Okay, now, there's something on Excel to demonstrate that. So let's go to Excel briefly. So what I have here is two columns of numbers I made. And what I did is there's a function in Excel called RAND, R-A-N-D, and then you put these parentheses here. And you can make adjustments. You can adjust this, but here, RAND like this basically gives you a random number. Once again, it's not exactly a random number. It's really close to being a random number since it's computer generated between 0 and 1. And they're also what's called uniformly distributed, meaning every number between 0 and 1 should be equally likely. Okay. So what I did here was I did 5 of these random numbers between 0 and 1, each between 0 and 1, everything being equally likely. So I'd expect the average of that, if it's equally likely, so the average would be about 0.5. You see here, the mean is actually about 0.39. Okay, there's only 5 numbers. Well, this next column, what I did is I did the same thing except with 50 random numbers. Let's go down here to the very bottom. I found the mean again. There, this time it's much closer to 0.5. Okay, so then if I did the same thing, did 100 random numbers, or 1,000 random numbers, or 1,000,000 random numbers of the same type between 0 and 1, all being equally likely or uniformly distributed, I expect then the more of these random numbers I generate and take the average, the closer the average should get to 0.5. That's the idea of law of large numbers. So the more you do something, the closer you get to the actual probability. This is also built in the way, once again, the way casino games work. Okay. That even though, once again, people are going to win, every now and then, you think of it as playing this game over and over many, many times, or many, many people playing it. In the long run, then this law of large numbers comes into play, where the more this happens, then the more people are likely to lose. The more you're going to lose, the more often you play the game, the more you should be likely to lose, more times than you win. So as you phrase that, each individual game is a small probability of success, but occasionally will succeed. But the more often you play the game, or the more number of people play the game, then you think about the average, more people lose on average than win on average. And that's how, for example, a casino makes money, is basically in the long run, more people lose than win, even though some people win big. And they still will make more money off those people who lose. So that's the idea of the law of large numbers, is very important and useful in that way. Okay. Now, let's talk a bit about unlikely events. So it's kind of what it sounds like. An event is unlikely if its probability is very small, maybe 0.05% or less, or 5% of the time or less. Okay. It says, for example, if you flip a coin 10 times, you get 2 heads, and usually low number of successes, or you get 8 heads, which would be usually high number of successes, the probability of that happening is very low. So the probability of flipping a coin 10 times, getting either 2 heads or 8 heads, is really small. And we'll, in future videos, you may see an explanation of how to calculate that probability. But one way you can think of unusual or unlikely with extreme outcomes based on z-scores. So if you may have seen another video on z-scores. So a z-score is tells you how many standard deviations you are from a mean. And basically, if a z-score is basically beyond 2 or more standard deviations from a mean, either a positive or negative direction, that's going to be really unlikely. So we kind of associate an unlikely probability event with something having a z-score of less than -2 or greater than 2. Now, let's also talk about the idea of a complement in probability. First, explain what a complement is. All right, so it says a complement of event A, denoted by A with a bar, we'll call it A bar, consists of all the outcomes in which event A does not occur. In other words, it says, in other words, A bar means not A. So let's kind of explain what this means. We'll use something called a Venn diagram. So let's say we have a box right here. And this box is what's called the universal set, or this box represents called the universal set. And the box is basically everything. Everything or everything that could happen. Okay. Let's say this spot right here, this circle, is event A. Okay. So these are basically the ways that A can happen out of everything that can happen. Then what's left is A bar. Okay. It's basically not A. All right. So here we have A, and then the rest of it is not A. Okay. So we look at an example here, a more concrete example. Let's give a dice. So here, think of this as rolling a fair die. Okay. So let's think this circle here, we get the idea, we get a 5. Okay, you roll a 5, and basically out here is what's left is you don't roll a 5. Okay, so you roll one of the other numbers. So here is our event A, we roll a 5, and then what's left is the complement. You think everything else can happen is a complement. We don't roll a 5, we will roll one of the other 5 numbers. Okay, of course, think the same way of coins and other kind of experiment. All right, so now why is this important? Well, mathematically, it's useful to understand. It says that if P of A is the probability of A happening, then the probability of oops, I apologize. Look, this is a typo. That's bad. So this should just be A. Sorry about that. So if P of A is a probability of A happening, then P of A bar, A complement, is a probability of A not happening. Okay. If the two events are complements, are also called what's called disjoint. Okay. So mathematically, we can say the following. So the probability of A complement is 1 minus the probability of A. Probability of A is 1 minus the probability of A complement. And basically, the probabilities of each add to each other. So let's think of this. Let's explain these mathematical ideas once again with some examples. Once again, we're going to roll a fair die. Okay. Let's call our event A. We're going to get, once again, get a 5. Then A complement is we're going to get another number. In other words, not get a 5. Okay. So we said before, I believe we said that before up here, mentioned it. We didn't explain why it was true entirely, but said the probability of getting a 5, since these are equally likely outcomes, or 6 possible outcomes, we said basically this is kind of the classical theoretical probability, 6 equally likely outcomes. So one of those, the outcome we want divided by the 6 number of outcomes we want is 1, divided by the 6 equally likely outcomes. So it's probably is 1 over 6. Okay. Now, this means, so then the probability of 5, getting a 5, we say is 1 over 6. Well, if I ask what's the probability of getting not 5 or some other number if I roll a fair die, in the same way, we have 6 possible equally likely outcomes. That's the number of our outcomes. Number of outcomes we want, there are 5 ways to get something that's not a 5, so that probability is 5, 6. So we can see then from these relationships, that the probability of not a 5 is 1 minus the probability of a 5, which is 1 minus 1, 6, which is 5, 6. Okay, because essentially this is everything that's left. So the probability of getting a 5 is 1, 6. Everything that's left is basically 1 minus that, since probability, we said the range is between 0 and 1. Okay. Now we'll also think about the probability of getting a 5. We can think of it the same way, is 1 minus the probability of not getting a 5. So 1 minus 5/6 is equal to 1/6. Okay, that also makes sense. If there are 5 ways to get something that's not a 5 out of 6 possibilities, what's left then is 1/6. Okay, and probably ways to make this more clear than anything is this next statement: the probability of a 5 plus the probability of not a 5. Basically, both these statements come from this one, is equal to 1. Or actually, before I say that, let me say, so that's going to be the probability of a 5 is 1/6 plus the probability of not getting a 5 is 5 out of 6. Of course, if you remember how to add fractions, you add those together, it gives you 6 out of 6, which is equal to 1. So basically, both these statements here come from this last one. That's kind of the most important one. And this is based on the idea of probability. If I say to you, I'm going to roll a die, I'm perfectly happy with a 5 or something's not a 5. What's the probability of that happening? Well, that's 100% or 1. I'm going to get either a 5 or not a 5. Same way if I say I'm going to flip a coin, I don't care what I get, a head or a tail, I'm happy with either one. Well, the probability of getting what I want is 100% because I'm either going to get a head or a tail. What's the probability of getting a head or a tail in one roll? That's 100%. The probability of getting a 5 and not a 5 in one roll of a die is also 100% or 1. Because either one of those is going to happen. And that's true if they're complements or what's called disjoint. Okay, so that's the idea of a complement. Now, I want to wrap up our discussion with some examples, and let's actually work with a deck of cards. Let's look at a standard deck of cards. Of 52 cards. So let's remember what we have in a standard deck of 52 cards. We have the numbers. Actually, I need to think about that just a second because I don't play cards all that often myself. So we have 3. Okay. So if I recall, then it's been a while. So we have the numbers. We have 4 called 4 suits. Okay. So we have diamonds, clubs, spades, and hearts. Okay. And so in these 4 suits, we have 13 each. All right. It's 13 times 4 is 52. We have 13 of each suit. Okay. Within each suit, then we have the numbers. That's why I had to remember, is there a 1 card? No, because basically then we have the numbers 2, at least I don't think there is, but if not, we'll just use this. The numbers 2 through 9, okay? Or 2 through 10, rather. 9 of those, 2 through 10. And then we have a jack, queen. Sorry, I'm also having trouble writing today. A king and an ace. So that should be 13. So numbers 2 through 10, then a jack, queen, king, and ace should give us then 13 in each one of those suits. Then 4 times 13 is 52. Now, let's look at some examples. And this is basically going to be kind of the second type, more of the theoretical probability. So drawing each card is equally likely. Okay, so the probability of each drawing each card is equally likely. All right, so let's look at a few examples. So number one, or let me kind of state this more generally. And so let's say that I want to find probability of number one, drawing the 5 of clubs. Okay, so probably drawing the 5 of clubs, we can write that as I'll put it as 5 of clubs, kind of the same way. Okay, well, the question is, so these are all equally likely. So this is much like the idea of flipping a coin or rolling a die. So there are 52 possible outcomes. Out of those 52, how many do I want? Well, there's only one 5 of clubs, so that is 1 out of 52. Now, number two, what if I said what's the probability of not drawing this same 5 of clubs? Okay, so the probability of not drawing the 5 of clubs. Well, we can think of that two different ways. So the probability of, I'll put it as 5 of clubs. I'll put it with this line over to indicate it's not that. Okay. The easiest way to do that is use the complement idea again. Because either think about those are complements. Either going to draw the 5 of, if we're going to draw some card, we'll either draw the 5 of clubs or a card that's not the 5 of clubs. So I can write this as 1 minus the probability of the 5 of clubs. And that's going to be 1 minus 1 over 52. And then that will be 51 over 52. Okay. Now, in each case, also, we can also approximate these. So if I just approximate this one, so 1 divided by 52, and that is approximately 0. I'll just 3 decimal places, 0.19, so less than 2%. Okay, and this probably this then is approximately, since the complement is about 0.981%, or not percent, about 0.81, or about 98.1%. So also let's think about this in a couple different ways. So this is about 1.9%. Remember, to change a decimal to percent, move your decimal place 2 places to the right. And this then is approximately 98.1%. So make sure you can think of probabilities as fractions, decimals, or percents. Okay. Now, if you notice, if we'd done it without using the complement, this would still be true. So if I don't want to, if I'm okay with drawing anything but the 5 of clubs, once again, we still have 52 equally likely outcomes. How many cards do I want? There's only one card I don't want, which is the 5 of clubs. There are 51 other possible cards, so that probably then is 51 out of 52. And this one, let's say, so this time with the probability of drawing the 5 of clubs, or not the 5 of clubs. Okay, well, that's the probability of, once again, the 5 of clubs, or I'll use the same notation again, 5 of clubs. Indicate not, well, as we've seen, basically you're saying, if you're going to draw some card, you're either going to get the 5 of clubs or not the 5 of clubs. And so that's going to be the probability. So once again, this complement idea, these are complements together, they're disjoint. And so that's going to be the probability of the 5 of clubs plus the probability of not the 5 of clubs. Write that with a line over it. And that's going to be equal to 1, because that's going to be 1 over 52 plus 52 over 50, 51 over 52, which gives us 52 over 52. 1. Okay. Now, Let's do a few more. This time, the probability of drawing a jack or a king. Notice these are also disjoint. Okay, so jack or a king. There's no intersection. There's no jack cards, both the jack and a king at the same time. These are disjoint. In future videos, we'll see how to do a case where there is some overlap. Like I said, if I wanted to draw either a heart or a jack, that's different. But here, these are disjoint. So let's think about this. So the probability of, I'll just put it J or K, just abbreviate that. Let's think about the possible outcomes I want. So once again, in one draw, so we have 52 possible outcomes I want. Okay, so how many jacks are there? Well, there are 4 jacks. I'd be happy with either one of those. So I'm okay with either one. So there are 4 jacks. Okay, then how many other cards? In other words, that of a probability is I'm happy if I get either any jack or any king. Okay, well, there are 4 jacks. There are 4 cards I want, but also there are 4 kings. There are 4 other cards that I want. And so that then will be then 8 out of 52, which we can reduce to, actually that's the same as 2 out of 13. And if you divide that, that's approximately, once again, if you round this off, 0.154. Okay, about 15.4%. Okay, so what this means is, once again, out of the 52 possible outcomes, there are 8 outcomes I'm happy with, I want. So the chance of getting that is 8 out of 52. Once again, this is a theoretical probability. Now, the experimental probability would be to, if you drew cards over and over again, or put them back, replace them over and over again. Okay, maybe draw cards hundreds, thousands of times. Then, for every, basically your ratio about 15.4% of the time, you should get either a jack or a king. That's that idea of the law of large numbers. You repeat it many times. Okay, and then finally, what's the probability or the probability of not drawing a jack or a king? Well, we'll write it this way. So jack or king. So once again, draw the line over to indicate this, not that. So that's going to be the complement. So that's going to be 1 minus the probability of a jack or a king. Their complements. And so that's going to be 1 minus 8 over 52. And that's going to be 44 over 52, which then is going to be, if you reduce that, 11 over 13. 11 over 13 should be approximately 0.846. So about 84.6% of the time as a percent. Okay. Now, make sure this makes sense. In the same way, if you thought about it without thinking of the complement, just thought about it directly in this way, 52 possible outcomes. Out of those 52 outcomes, how many are not a jack or a king? Well, if there are 8 of the 52 are a jack or a king, there are 44 that are left that are not. So your probability then is 44 out of 52, or about 84.6%. Once again, the idea of law of large numbers, if you drew cards over and over again, hundreds, thousands of times, about 84, almost 85% of the time, you should get a card that's not a jack or a king. Okay, so what we learned today are the basics of probability, the basic concepts, definitions, how to calculate basic probabilities, and also understand the range of probabilities, the law of large numbers, and also how complements work. Thank you. Have a good day.